Imagine a massive new development is proposed in your community, maybe a huge mine or a new factory. How do you objectively measure its impact? How do you even begin to know what normal looks like before anything actually changes? That's something I've definitely wondered about. Today, we're diving deep into this idea of the baseline, that fundamental understanding of the existing environmental and social conditions before a major project even starts.
It's an absolutely critical step, yes. And our mission today really is to unpack the pretty meticulous process involved in establishing this baseline. We'll look at everything from figuring out what data is actually needed to making sure it's credible, and then crucially, turning that raw stuff into actionable insights. It's often overlooked by the public, this preliminary work, but honestly, it's vital for any kind of responsible development.
Yeah, absolutely. We've been digging into some fantastic material for this deep dive, mostly drawing from the expert analysis in Mining and the Environment by Dr. Karl-Heinz Spitz and John Trudinger. So you're getting a real shortcut to being well-informed here. Now, when we talk about a baseline in the context of, say, a new mine, what exactly are we talking about?
Okay, at its core, the baseline is like a comprehensive snapshot. It captures the existing environmental and social conditions in a specific area. But importantly, it also includes an assessment of the likely changes that would happen anyway, even without the project. Think of it as having a dual purpose. First, it lets us accurately assess the changes caused by the project itself. And second, it gives us benchmark data, a really critical reference point for ongoing monitoring and for verifying those impact predictions made way back at the start.
Okay, that makes perfect sense. So how much data are we talking about for this snapshot? Is it like you just keep collecting terabytes, or is there a point where you say, okay, that's enough?
No, definitely not about hitting a data cap. There's no fixed number at all. The amount of data you need. It depends entirely on the specific environmental situation, the kind of project being proposed, and really importantly, the concerns raised by stakeholders during that early planning or scoping phase. The book actually highlights a great test. They call it the so what test for data relevance. Basically, if you can delete a piece of data from your report without really damaging your interpretations or assessments, then it probably shouldn't be in there. Unless, of course, it's legally required. Maybe a stakeholder specifically asked for it. A classic example they give is solar radiation data. It often gets included in baseline reports just because weather stations measure it, but it's rarely, if ever, actually used in a mine's impact assessment. It's often just data for data's sake.
Data for data's sake. That's a really critical distinction you're making, moving beyond just collecting stuff to making it useful. The source material points out this is a main challenge, differentiating raw data from actual information. Like, what does a list of water chemistry elements really tell us about the health of a river beyond just being a list?
Exactly. That's the fundamental challenge. Raw data, whether you collect it yourself in the field, primary data, or get it from existing sources, secondary data, it only captures a very narrow slice of what's going on. The real goal, the aim, is to assess that raw data, to derive information from it about the actual state or condition of the environment and the social processes happening there. It's about turning numbers into meaning, understanding what those numbers signify for the ecosystem or the community. And like you said, that conversion isn't always simple, but it's absolutely essential.
So how do we make sense of all that raw data, turn it into something meaningful? We're used to economic indicators, things like GDP or unemployment rates that simplify complex stuff. But the source makes a really powerful point. Indicators aren't just for economics, they exist for all parts of the environment. And this is where it gets really interesting.
It really does. Indicators are absolutely crucial. Why? Because they give us a way to present incredibly complex information simply, clearly, in a manageable way. And think about it. It's just impractical, maybe impossible, to measure every single environmental parameter, like testing for every element in the periodic table in a water sample. Forget it. So the practice is to select key indicators, the ones that best represent a complex ecosystem or environmental issue. They quantify and simplify information, both for the decision makers and for the public. Often they combine multiple data points into maybe just one number. That makes them far better analytical tools than just looking at raw data alone. And these indicators, they aren't just for setting up that initial baseline. They're really embedded in the whole interpretive framework. Repeated measurements of these chosen indicators. That becomes your ongoing monitoring program during the mine's operation. It lets you consistently compare back to that initial benchmark to detect and quantify any changes over time.
That makes a lot of sense. But okay, with so many things you could measure, how do you pick the right indicators? Especially when you're dealing with really diverse, complex environments. Sounds a bit like finding a needle in a haystack.
It can feel that way, definitely, which is precisely why having frameworks is so important. The book details several really powerful approaches for selecting indicators. One big one is the OECD, that's the Organization for Economic Cooperation and Development, their Pressure State Response Framework, or PSR. This looks at human activities that exert pressures on the environment. Then it looks at the resulting state or condition of the environment. And finally, the human and natural responses to those changes. It gives you that whole cycle, cause, effect, reaction.
Okay, pressure, state, response. Got it.
Then there's another approach, Segnestam's project-level indicators. This one really pushes beyond just tracking what the project does. It classifies indicators across a whole spectrum, from the resources we input for management, to the processes we use, to the outputs like emissions or waste. But crucially, it goes further to outcomes, the actual environmental changes, like shifts in biodiversity. And then even further to long-term impacts, maybe demographic shifts in a community. The key insight there is that just measuring outputs, like how much discharge, isn't enough. You have to measure the real change happening in the environment or the community. People care about the end results, right?
Not just the factory's output, but what it actually does to the river or the air.
Precisely. Then there's another useful distinction, alarm versus diagnostic indicators. Think of an alarm indicator like a smoke detector in your house. It's usually a small set of easily monitored low-cost measures. Things like water levels in tailings ponds or maybe pH values in discharged water. They give you an early warning if something might be going wrong. If an alarm indicator crosses a certain trigger level, it doesn't tell you why there's a problem, but it kicks off the need for more costly, more time-consuming diagnostic indicators. Those are designed for a much deeper analysis to figure out the underlying causes. It's about triggering the right level of investigation at the right time.
So like a tripwire system.
Yeah. And finally, there's the difference between lagging and leading indicators. Lagging indicators are like looking in the rearview mirror. They measure results after they've happened. Things like tons of waste produced or the number of fines paid. They tell you about problems that have already occurred. Leading indicators, though, are proactive. They look forward. They measure the implementation of practices that are expected to lead to better performance. Like, how many internal compliance audits did we conduct this quarter? The big advantage. Leading indicators let you take corrective action before problems show up in those lagging indicators. You can fix things proactively.
Proactive versus reactive. Makes sense.
So when you're actually choosing indicators, the bottom line is they have to meet several criteria. They need to be scientifically valid and verifiable so you can trust the data. They need to be practical and cost-effective to monitor, otherwise you just won't do it consistently. And they absolutely must be relevant to management and the community. They should provide early warning, help with reporting, and reflect things people actually value. The key advice is, be selective. Use smaller, chosen sets. Trying to track too many indicators can just dilute their usefulness and overwhelm everyone involved.
That's a really clear breakdown. It really helps distill that complexity. But this raises another question. How creative can you get with indicators? The material mentions using wildlife as early warning signals, which sounds absolutely fascinating.
Well, it really is. And there's a distinction here, too, between indicator species, sometimes called bioindicators, and sentinel species. An indicator species is basically a plant or an animal whose presence or absence, or maybe its general condition, tells you something about the environmental conditions in that area. They signal the biological health of an ecosystem, and they can help direct mitigation efforts. The classic example is fish for water quality. They're great indicators because they live their whole life in the water. Different species have different tolerances to pollution. They're relatively easy to collect. They live for several years, and they're usually easy to identify. So just by looking at the fish, what kinds, how many, how healthy they look, you get a really clear living picture of the water quality.
Like a living litmus test.
Yeah. Now, sentinel species are slightly different. They provide an early warning of potential human health impacts. Organisms high up the food chain, top predators, often reflect human exposure to contaminants because, surprisingly, their physiological functions can be quite similar to ours. For instance, if a chemical is neurotoxic to birds, chances are it's neurotoxic to humans too. If it messes with hormones in fish, estrogenic effects, it likely does the same in humans. This is where that old phrase, canary in the coal mine, comes from. Canaries were literally used to detect carbon monoxide. Or think about lichens and mosses being sensitive indicators of sulfur dioxide pollution.
Wow. Okay, moving from the natural world to the human one, evaluating the social baseline seems even trickier. How do you measure things like community well-being or economic opportunity in a way that really captures what's happening on the ground?
You're absolutely right, it is more difficult. Because standard statistical indicators, like income averages, often give you only a very narrow view. They miss a lot of the nuance. The book really stresses the importance of designing these social indicators jointly with the community itself. This isn't just about being nice. It ensures the indicators are actually relevant to the people living there. It helps the community feel ownership, become stewards of monitoring those indicators. And it makes communicating the real benefits or the downsides of a project much easier and more transparent. When the community helps define what good looks like, they're more invested in tracking it.
Collaboration is key then.
Absolutely. And speaking of creative social indicators, the source shares this really fantastic anecdote. It's Case 9.2, satellite dishes as indicators of disposable income. Apparently, near a gold mine in Indonesia, instead of relying only on complex economic surveys, the mine staff found a super simple, easily measured, and visually powerful indicator. They just counted the satellite dishes on village houses. Over 7 years, the number of dishes in one village went from just 4 to 95. That provided this undeniable visual proof of increased disposable income and also gave some sense of how it was distributed. They also looked at other simple things like home extensions, more motor vehicles. The surprising thing here is that sometimes the best insights come from these really simple, observable things, not always complex statistical models.
That's an incredible story. So simple, so effective. Okay, so before you even start collecting all this data, whether it's counting satellite dishes or measuring water pH, you need a solid plan, right? The source introduces this concept of environmental scoping.
Absolutely critical. Scoping is that initial process. It's where you determine the context and the extent of the issues that need to be covered in the full environmental assessment. It literally defines the scope of the information you'll need and outlines the detail for the baseline surveys that follow. The big challenge, as the source points out, is that scoping needs to be both comprehensive and rapid. You need to be thorough, but you can't let it drag on forever.
How do you do that? Be comprehensive and rapid.
It involves pulling together information from lots of places. There are regulatory requirements, sometimes expensive public participation. You use tools like desk studies, reviewing existing reports and maps, analyzing satellite imagery, talking to experts, and, crucially, compiling existing secondary data. That includes invaluable traditional knowledge from local communities. Typically, it involves an initial site visit too, but usually more for observation and talking to people, not full-on field sampling at this stage.
Okay, and what's really fascinating here, the material says scoping can help identify fatal flaws or showstoppers really early on. What does that mean for a project's success, or maybe failure?
This is probably one of the biggest benefits of doing scoping well. And frankly, it's a massive potential cost saver for the project proponent. By identifying major potential problems early, things like maybe there's just no feasible way to get heavy equipment to the site, or it's right next to a highly sensitive protected area, or there are complex unresolved land rights. By finding these early, you can avoid incredibly costly delays and redesigns later on. The book has a great illustration showing how your ability to fix problems cheaply diminishes rapidly as planning progresses. Finding a showstopper during scoping means you redesign on paper, which is far cheaper than trying to re-engineer something once construction is planned or even started.
Makes sense. Fix it before you build it.
Exactly. Good scoping also helps keep the eventual environmental assessment documents focused. You concentrate only on the significant issues, not every tiny detail. And it's particularly vital for understanding the social side, the community setting, the potential costs and benefits for local people. It's basically your early warning system for the whole project's viability, both environmentally and socially.
So where does all this initial scoping information come from?
It's diverse. You need a good understanding of the proposed mine's activities and their likely impacts. And of course, you need to understand the nature of the environment itself, the physical, biological, social aspects. Information comes from government agencies, from NGOs, academic studies, and increasingly from tools like Google Earth, which allow for amazing virtual site tours even before you set foot there.
But it's not just about what you find online, right? The source really stresses the value of actually going there, the site visit, and listening to local people, maybe tapping into traditional knowledge.
Oh, absolutely correct. Desk studies give you a foundation, but nothing replaces a site visit for verifying information, what we call ground truthing, seeing it with your own eyes. And it provides those crucial opportunities to access local environmental knowledge, especially from indigenous communities who often have generations of experience living in and understanding that specific environment. Case 9.3 illustrates this perfectly. A new investor was looking at a chromite mine in Vietnam, where mining had happened on and off for over a century, plus recent illegal mining. They needed a really comprehensive baseline. And the surprising nugget here, a robust baseline wasn't just about assessing future impacts, it was about creating a kind of legal shield. It protected the new, responsible investor against potential future claims, maybe false claims of pollution that might have actually come from those past activities or the illegal miners. A solid baseline was their best defense.
So it's insurance, too, in a way.
In a very real way, yes. The main output of this whole scoping process is usually a scoping report. This document essentially becomes the terms of reference for the main environmental and social impact assessment, the ESIA. It's like a detailed roadmap. It outlines the approach, the data needed, the methods to be used for all the future studies. It describes the project, the institutional setting, the environmental setting, the social setting, and lists recommended studies to fill any information gaps identified during scoping.
Okay, so the scoping's done, you've got your roadmap, and now it's time for the actual baseline surveys on the ground. Is it all just about collecting numbers, or is there more to it when you're out there in the field?
It's definitely more than just numbers. Baseline surveys usually use a combination of qualitative and quantitative methods. So qualitatively, you might have a plan view map showing where you made observations. Quantitatively, you might have a detailed, scaled vegetation map that actually quantifies the area covered by different plant types. Fieldwork is, of course, essential for getting that quantitative data. And while we often talk about baselines being snapshots in time, it's really important to consider relevant long-term data too, like climate records going back years. That gives context to your snapshot. A single dry season snapshot might look very different from the long-term average, right? Context is key. And the book really hammers home the importance of planning here. It says something like, planning is the first step to successful field work, like a foundation to a building. Poor planning often produces shaky results. Good planning isn't just about being efficient, saving time and money. It's fundamentally about ensuring your objectives are met and that the data you collect is actually robust and reliable.
So what are the main objectives then? When the teams go out for these on-the-ground surveys, what are they ultimately trying to understand?
There are several key goals, all feeding into creating that comprehensive picture we talked about. First, it's about deeply understanding the affected environment and the people, gaining real insight into the communities and the environmental components, air, water, land, plants, animals that might be impacted. This often involves talking with local people to identify resources that are particularly significant to them. Things that might not show up on a standard map, like a culturally important site or a specific medicinal plant gathering area.
That local input seems crucial.
It is. Second, biodiversity-defined studies are critical. This means meticulously characterizing habitats, but also identifying any rare, endangered, vulnerable, or near-threatened species. You'd reference international lists like the IUCN Red Data Book or CITES appendices, which track these species globally. You need to know not just if they're there, but where they are, their distribution, and what they need to survive so you can figure out how to protect them. Third, documenting traditional knowledge. As we mentioned, this local, often indigenous knowledge is invaluable. It can provide insights into historical environmental conditions, long-term trends, resource use patterns. It should be integrated respectfully and cross-referenced with other data sources where possible.
Okay, so understanding the place, the species, the local knowledge. What else?
Fourth, baseline surveys help identify existing natural hazards and project constraints. Is the area prone to landslides, intense rainfall, earthquakes? Are there existing protected areas nearby? Unstable slopes? Understanding these site characteristics early on is vital because they can directly affect the mine's design and operation. Again, finding showstoppers here during the baseline phase is far better than discovering them later when changes are expensive. Fifth, quite simply, the baseline provides the essential basis for impact evaluation. You just can't assess the change caused by a project if you don't have a clear, documented picture of what things were like before.
The before picture.
Exactly. Sixth, and this is really important for the long term, it's about defining reference points for future monitoring. This usually involves setting up control sites or reference sites. These are areas that are similar to the project site in terms of environment, but are located far enough away or upstream, so they won't be affected by the development. These control sites allow you to differentiate between changes caused by the project and changes that are just natural variations or due to other factors, like regional climate shifts. Though finding good control sites, especially for human communities, can be tricky. Things like people moving into an area because of the project in migration can easily mess up simple comparisons if you're not careful.
That makes sense, trying to isolate the project's effect.
Seventh, the baseline data also directly provides data for project design. It's not just for the environmental assessment, The engineers use it too. Things like detailed climate data helps them decide where to best locate facilities that might emit air pollutants. Geotechnical data about soil stability and earthquake risks informs how they design buildings and waste storage facilities to be safe. Eighth, it helps in identifying existing environmental liabilities. This is about uncovering any pre-existing contamination or degradation from past activities, maybe old artisanal mining or illegal logging. That ties back to the Vietnam chromite mine case, ensuring the new company isn't blamed for old problems.
Right, the due diligence aspect.
And finally, baseline surveys are key to identifying data gaps. They pinpoint areas where maybe more study is needed. Perhaps you need more detailed information for planning mine closure and rehabilitation way down the line, or for managing a particularly sensitive habitat.
Okay, this sounds incredibly involved and often in pretty remote or challenging places. What about the health and safety of the people actually doing this field work? The source has that stark line. Field work is either safe or it is not.
It is stark, and it really underscores that health and safety have to be the absolute top priority. There's no compromising on this. The standard process involves a four-step risk assessment. First, you identify all the potential hazards: physical, biological, chemical, security risks. Second, you assess the likelihood of those hazards occurring and what the consequences would be. Third, you implement control measures to eliminate or minimize those risks. And fourth, you continuously monitor and review how effective those controls are and adjust as needed. It's a constant cycle. Key things to consider in planning include having a clear chain of command, ensuring the team size is appropriate for the risks, checking people's fitness for the conditions, having reliable communication systems, often satellite phones or radios in remote areas, and making sure adequate first aid and emergency response plans are in place.
It sounds like planning for the worst, hoping for the best.
Pretty much. And the book gives a really vivid example in Case 9.4, Health and Safety Planning, Preparing for the Unexpected. It describes an incident in remote Kalimantan, Indonesia, where a team member had a severe reaction to a poisonous plant. But because they had planned properly, they had satellite communication, emergency helicopters on standby, even an on-site paramedic. The person was evacuated incredibly quickly, got hospital treatment, and recovered fully. The surprising nugget there is just how critical that upfront professional planning was. It literally turned a potentially life-threatening situation into a manageable incident with a good outcome. Preparation is everything.
Wow. What about getting around? Field transport must have its own risks.
Absolutely. For vehicles, the rules are strict. Only trained and licensed drivers. Vehicles need to be well-maintained. Often, diesel 4x4s are preferred for tough off-road conditions. Proper loading is important, avoiding overloading. Preventing driver fatigue is key, especially on long drives. And drivers need to be super cautious, especially with unpredictable traffic or near settlements. For boats, especially offshore, you need compliance with maritime laws, proper licenses, essential safety gear like life jackets and flares, and reliable radio communication. The standard is usually a minimum of 2 competent swimmers on board for any boat work, and thorough weather checks before setting out are non-negotiable. Some companies, the book notes, actually exclude things like scuba diving from their services altogether because the risks are considered too high to manage reliably.
And security, that must be a concern in some areas.
Definitely. Basic security rules include things like trying not to appear wealthy, avoiding travel at night if possible, and crucially, never working alone in the field. The minimum is usually 2 people, plus a local guide who knows the area and local context. And it's essential to coordinate with local authorities, police, or community leaders so they know who you are and what you're doing. Case 9.6 from Halmahera Island in Indonesia provides a really stark illustration. Environmental teams doing scoping work there actually required military escorts because of ongoing violent religious unrest in the area at the time. It shows that security isn't just an add-on. Sometimes it has to be absolutely central to fieldwork planning.
That's sobering. Okay, so after all this immense effort, the planning, the safety protocols, the fieldwork itself, how do you make sure the data you've collected is actually credible and useful? What makes data trustworthy, especially when it might be challenged later?
Credibility really boils down to 2 main things: meticulous documentation and a rigorous quality assurance and quality control plan, or QA/QC plan. This means having detailed field sheets with clear instructions for recording everything, and having standard operating procedures SOPs for every single sampling and analytical method used. Everything needs to be done consistently, reproducibly, and documented clearly.
SOPs sound crucial.
They are, and there's always this interplay between measurements you take right there on site, in situ measurements for things like water temperature or pH, and samples you send off for laboratory analysis. Instrument calibration is critical for both. If your pH meter isn't calibrated correctly, your field data is useless. But the book points out something interesting. Laboratory analyses probably cause more confusion, uncertainty, and disputation than any other part of the baseline data collection process.
Really? Why the labs?
Often it comes down to issues with reproducibility. Can different labs get the same result from the same sample? Are their detection limits low enough for environmental work? This is why independent laboratory accreditation schemes are so valuable. Things like Australia's NADA or similar bodies elsewhere, they provide an external check, a stamp of reliability on the lab's procedures and results.
So using an accredited lab helps build trust.
Definitely. And here's another fascinating detail. Case 9.9, Freeport's environmental laboratory in Indonesia. Freeport, a massive mining company, actually built its state-of-the-art environmental lab over 100 kilometers away from its mine and processing plant. And the surprising reason, to prevent cross-contamination. Think about it. Environmental labs are measuring contaminants in incredibly tiny amounts, parts per billion, sometimes even parts per trillion. Metallurgical labs at the mine site are measuring metals in percentage levels vastly higher concentrations. If those labs were too close, the risk of microscopic dust from the processing plant contaminating the environmental samples would be huge, making the environmental results completely unreliable. Building the lab far away showed an incredible commitment to data integrity.
Wow, 100 kilometers away. That's dedication to clean data.
It really is. And it comes back to that theme of measuring what matters. Data collection always has to be specific to the site and the project. There's often a trade-off you have to make between coverage, sampling lots of locations, to get a broad overview of an area, and intensity, focusing on fewer sites, but studying them much more deeply, maybe sampling more frequently or analyzing more parameters. The best choice depends on the project's nature, its size, the questions you're trying to answer. The book shows how water monitoring locations, for example, often evolve and link together throughout a mine's life, emphasizing that baselines aren't just a one-off snapshot. They're the start of a long-term monitoring story.
It connects forward.
Exactly. And of course, using skilled, experienced experts for this work is vital, but also leveraging local expertise wherever possible. Local people often have insights that external experts might miss. For the social science side, data collection methods often involve reviewing existing data census reports, health statistics, but also directly asking questions through surveys and interviews and using structured observation techniques. Systematic scheduling is important here too. You need to account for seasonality. Wet season versus dry season behaviors might differ, even daily variations, diurnal patterns. And technology is constantly changing things. Motion-activated infrared cameras are now common for wildlife surveys. Drones are increasingly used to survey difficult-to-access habitats like cliffs or dense forests. Each tech has its pros and cons, of course.
Okay, you've done the field work, you've got QA/QC, maybe your lab is 100 kilometers away. You have all this meticulously collected, verified data. But like we said earlier, raw data doesn't mean much until you turn it into information. So how do you bridge that gap? How do you get valuable insights, not just piles of numbers?
Right, the ultimate goal is exactly that. Converting data into useful information for decision-making. The first step is distinguishing between findings and conclusions. A finding is an objective observation from the data. Turbidity levels measured downstream of the exploration site were consistently higher than upstream during the survey period. That's a finding. A conclusion is the explanation, the interpretation of that finding. The higher downstream turbidity is likely due to natural bank erosion observed during heavy rainfall events in the upper catchment, as visual inspections revealed no evidence of runoff from the exploration site itself. That's a conclusion.
Finding is the what, conclusion is the why.
Exactly. And several key questions help guide that interpretation process. How does this new data compare to historical data or established reference points like water quality guidelines? Are there clear seasonal differences? Did any specific natural events like a flood or a drought influence the results during the survey period? Do you see clear changes as you move from upstream to downstream? Do different parameters seem to correlate? Does metal concentration increase when pH decreases? And critically, do the visual observations made in the field actually support the numerical data? If the water looked clear but the lab says turbidity is high, you need to figure out why there's a disconnect.
Connecting the dots.
Precisely. Another powerful approach is to try and analyze the data holistically. Fit it into established ecological models or conceptual diagrams. The force mentions things like understanding data within the context of the atmospheric energy cycle, the hydrological cycle, pollution transport pathways, biogeochemical cycles, food webs, trophic cycles, even demographic, economic, and social cycles. Thinking about how your data fits into these bigger systems gives you a much richer understanding than just looking at isolated numbers.
But what about variability? You mentioned natural systems fluctuate. How do you deal with that uncertainty?
That's a constant reality. Natural systems, rivers, forests, animal populations are inherently variable, and the process of sampling and analyzing introduces even more variability and uncertainty. We can't eliminate it, but we use statistical tools to understand and quantify it, calculating means, medians, ranges, standard deviations, conducting trend analysis. These help us estimate the contribution of natural variability versus potential project effects. It's about making informed decisions despite the inherent fuzziness.
And reaching conclusions, especially if they might be unpopular.
The key principle is that conclusions must be supported by the data, even if they are controversial or don't fit a preconceived narrative. Case 9.NZ. Sometimes conclusions are controversial, provides a really compelling example here. This involved the Newmont Minahasa gold mine in Indonesia. There were serious allegations made against the mine, claiming mercury and arsenic pollution was harming the community and the marine environment. However, subsequent independent scientific analyses, reviewed by international panels, consistently failed to find evidence supporting these specific claims related to mine impacts. The company was eventually acquitted in court. The powerful, perhaps surprising nugget here is that rigorous, transparent, independently verifiable science is crucial, especially in contentious situations. It highlights the importance of checking everything. Was the sampling representative? Were the analytical methods sensitive enough? Were there other potential sources of contaminants? Trustworthy data and sound interpretation have to be the foundation, even when the conclusions are difficult.
That's a really important point about scientific rigor. Finally, let's touch on the cutting edge. How do technologies like remote sensing and geographic information systems, GIS, fit into this whole baseline and monitoring picture? They seem to be everywhere now.
They've really become standard tools, absolutely revolutionizing how we handle spatial information in environmental science. So remote sensing broadly is the science of getting information about the Earth's surface without actually touching it, primarily interpreting images taken from aircraft or satellites. It helps us map physical geography like topography, different types of vegetation or habitats, water bodies, land use, and geographic information systems, or GIS, are the powerful computer systems we use to store, integrate, analyze, and importantly, display all that spatial data. Advances in computing power, plus the sheer explosion of available digital data from sources like Landsat satellites, spot, high-resolution imagery like Iconos, and readily accessible platforms like Google Earth or elevation data like SRTM, all this has made GIS and remote sensing indispensable.
So what can they actually do in this context?
GIS provides this unique, incredibly powerful platform for dealing with all the spatial aspects of a big project like a mine, which obviously covers a large area. It lets you produce highly detailed, informative maps very efficiently showing topography, different habitats, rivers and lakes, settlements, roads, land ownership, everything layered together. But beyond just making maps, GIS has really powerful analytical capabilities. You can analyze proximity, how close is the project to sensitive areas. You can model runoff pathways. You can calculate habitat fragmentation. You can overlay different data sets to see relationships.
Sounds incredibly powerful. Any pitfalls?
The main caution is that the crisp, clean, seemingly precise maps generated by GIS might create a perception of accuracy that doesn't always reflect the reality of the underlying input data. It's crucial to always understand the source, the age, the scale, and the inherent accuracy limitations of the data you're putting into the GIS. Because the map is only ever as good as the information it's built upon. Garbage in, garbage out still applies.
Good point. Understand the source data.
But the benefits are immense. Identifying site-specific constraints and opportunities really early in planning. Verifying field data using satellite imagery to check observations made on the ground. Dramatically improving environmental mapping and understanding complex landscapes, assisting environmental monitoring during operations, tracking changes over time, and powerfully documenting environmental change. GIS is fantastic for showing before and after scenarios or tracking the expansion of disturbed areas versus rehabilitation efforts. It helps you differentiate land use changes caused specifically by the mining project from changes caused by natural processes or maybe other human pressures like agriculture expanding nearby. In essence, you can think of GIS as potentially being the central knowledge base for a project, a system that concisely stores, analyzes, and communicates all the environmentally related spatial data throughout the entire life of the mine, providing this evolving dynamic picture.
Wow. What an incredible journey we've taken today. Seriously, from just defining what a baseline is to harnessing the power of sometimes surprising indicators like satellite dishes, understanding the absolute strategic importance of good scoping, diving into the meticulous work of field surveys, focusing on that non-negotiable aspect of health and safety, and finally, exploring the art and science of turning raw data into truly meaningful information using sophisticated tools like GIS. Is clearly far more complex and fascinating than just collecting some data.
It really is.
Yeah.
And it highlights that understanding a host environment isn't just a technical exercise of collecting data points. It's about building a truly comprehensive living picture, its physical environment, its ecosystems, its people, its history, its potential future. And this raises, I think, a really important final thought for everyone listening. In a world where we see increasing pressure for development, and given the tools and the knowledge we now have, how do we ensure that this kind of detailed, proactive, comprehensive approach to baseline studies becomes the universal standard for all large-scale projects everywhere, not just best practice for the companies that choose to do it well?
That's a powerful question to leave us with. What stands out to you from today's deep dive? How might you apply this kind of deep dive thinking in your own work or just in how you understand the world around you? Until next time, keep digging deeper.